Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is planar graphs, and we will prove a necessary condition for graphs being planar. I'm going to remind you what planar graphs are and what Euler's formula for planar graphs are. I have two other videos that go in more depth for both of those things. Then I will tell you about the Girth of the graph, and we will prove a theorem with proof that for a connected simple planar graph, the number of edges must be always less than or equal to g divided by g minus 2 times v minus 2, where g is the Girth and v is the number of vertices and e is the number of edges. As a consequence, we can prove that the complete graph on 5 vertices, K5, and the complete bipartite graph on 3 and 3 vertices, K3, are non-planar. We also will discuss the fact that subdivisions of these graphs are also non-planar. And then without proof, we will tell you about the amazing Kuratowski theorem that gives a necessary and sufficient condition for graphs being planar. What are planar graphs? A planar graph is a graph that can be drawn in the plane with no edges crossing. For example, this is a planar graph. None of the edges are crossing each other in this particular drawing. Such a drawing of a graph, a drawing where edges are not crossing, is called the planar drawing of the graph. I could draw this graph with its edges crossing, but as long as I don't, that's called a planar drawing of the graph. For connected simple planar graphs, Euler's formula, the amazing Euler's formula, tells us that the number of vertices minus the number of edges plus the number of regions is 2. Regions are the connected components of the complement of the graph. This is an amazing formula. It has lots of uses and lots of generalizations. And in this lecture, we will see some of its uses. I have a whole video on Euler's formula, proving it. I have another one on tilings of soccer balls, where I give another proof of Euler's formula and use Euler's formula for investigating different ways that you can tile a soccer ball. Here we will use it for talking about planarity. In this particular example, we have 8 vertices, 10 edges, and 4 regions, and v minus e+r is 2. Euler's formula is for connected simple planar graphs. This is a necessary condition for a graph to be planar. If you are a planar graph, then you must satisfy this. But this is unsatisfactory because it involves regions. And to be able to count the number of regions, you have to have a planar drawing of the graph. If a graph walks through the door and you don't know if it's planar or not, and the drawing that you have has a lot of crossings, you won't be able to say what the number of regions are. You will first have to say, can I draw it in a way with no edges crossing? And then I can count the regions. But if you could draw it without edges crossing, then you would know it's planar already. So we want a relationship that doesn't involve the number of regions. Is this graph, for example, planar? If some graph walks through the door, it's not necessarily clear whether or not it's planar or not. This graph, for example, is the same graph as I had shown you before, but just drawn slightly differently. But the question is that how can we tell if the graph is planar? Let's look at some examples. The complete bipartite graph, where one part has 2 vertices and the other part has 3 vertices. Is that planar? The normal way of drawing K23 is not telling me whether the graph is planar or not because there are edge crossings. But I can draw it differently. This is also K23. The 3 vertices in the middle are one part, and the other 2 vertices are the other part. And every one of the ones in the middle is connected to the other 2. So this is K23, that no edges are crossing, and so K23 is planar. What about K4, the complete graph on 4 letters? The usual way you might draw K4, again, has a crossing. But you can draw it differently, and you can see that, yes, K4 is planar. But as the graph becomes more complicated, it's less likely that it'd be planar. Next question might be, what about K33 or K5? Now, this is K33 and there is K5. And you might want to try to see if you can draw those on the plane without edges crossing. Spoiler alert, you can't. But we want a proof of that. It might be that you can convince yourself that, no, there's no way to do that. But then I might say, well, maybe you're just not smart enough. And if you were clever enough, you could come up with a way of doing it. We want ironclad proof that this cannot be done. I need to tell you what the Girth of a graph is. A general graph means a graph where you allow loops and double edges. The Girth of G is the length of a shortest cycle in G. A cycle is when you start at a vertex, go through edges and vertices and come back to where you started without repeating any vertices and edges. And the shortest one gives you the Girth. And I say a shortest cycle because there might be several shortest cycles. The Girth of a forest, a graph that doesn't have any cycles, is infinite. For example, this is the Petersen graph. What is its Girth? The Girth of this graph is actually 5. And for example, here's a cycle of length 5. You can go from 1 to 6 to 8 to 10 to 5 back to 1. And you can't find any cycles of length 4, 3, or smaller. And so the Girth of this graph is 5. A related thing is the diameter. We are not going to use the diameter, but this graph, Petersen graph, is interesting because it has actually a small diameter and a large Girth. The diameter is 2. What's the diameter? The diameter is the longest distance between two vertices. What's the distance between 1 and 3? Well, you can go to 1 and 3 several different ways. For example, you could go from 1 to 6 to 9 to 4 and then 3. But if you do that, you're taking your time. You're not going the most efficient way. And that doesn't tell you the distance. The most efficient way to get to 3 is go from 1 to 2 to 3. And then you have a path of length 2. And the distance between 1 and 3 is 2. So you look at every pair of vertices. You look at all their distances. And you pick the largest one, and that's the diameter. And in this graph, the diameter is 2, which means that in this particular graph, if you pick any two vertices, either they're adjacent, either there's an edge between them, or if they're not, you can go to the other via one other vertex. And this graph is interesting because even though the diameter is so small, the Girth is relatively large. The theorem that we want to prove for planarity is that for a connected planar simple graph with finite Girth, the number of edges is less than or equal to g divided by g minus 2 times v minus 2. What are these things? Where v is the number of vertices, e is the number of edges, and g is the Girth of the graph. And the nice thing about this theorem is that it doesn't involve the number of regions. You can figure out what e is, v is, and g is, no matter what drawing of the graph you have. Regardless of the drawing of the graph, you can check this condition. And if it's not satisfied, then the graph is not planar. If it is satisfied, then you know nothing. Then you have to go back to the drawing board and try something else. Note that g divided by g minus 2, if you divide top and bottom by g, is the same as 1 over 1 minus 2 over g. This means that if you put in a bigger g, then 2 over g becomes smaller. So you're subtracting something smaller from 1. So the denominator becomes bigger. And so that means that the whole thing, g over g minus 2, becomes smaller. So the bigger g makes this coefficient smaller, and that will make a tighter restriction on E, which means that the bigger the G is, there's more restrictions on the number of edges. The Girth of a connected planar simple graph, the smallest that it can be, is 3. And so that puts the least amount of restrictions. That's the loosest restrictions on the number of edges. And in that case, what you get if you put instead of G3, you get E must be less than or equal to 3v minus 6 for all. Even if you don't know what the Girth is, for all connected planar simple graphs. The next step up is if your graph does not have Girth 3, but has Girth 4 or 5 or 6. And so it means it doesn't have any triangles. If you have a triangle 3 connected planar simple graph, then you know that G is at least 4. And if you put 4 there, you get that coefficient is 2, and you will get that the number of edges is less than or equal to twice the number of vertices minus 4. 2 times v minus 2, which is 2v minus 4. This is a theorem that we want to prove, but let's first try to see what we can do with it if we do prove it. The first thing I'm going to show you is that we can use this to prove that K5, the complete graph on 5 vertices, is not planar. We know for any connected planar graph, the number of edges is less than or equal to 3v minus 6. Let's just check that for K5. K5 has 5 vertices, and the number of edges is 5 choose 2 is 10 edges. And 15 minus 6 will be 9, and 10 is greater than 9. It's not less than or equal to 9. And so that contradiction tells us that this could not have been a planar graph. We can also prove that K33 is not planar. Now, again, the number of edges must be less than or equal to 3v minus 6 for any planar graph. In this case, we have 6 vertices and 9 edges. But 9 is less than or equal to 3 times 6 minus 6. 3 times 6 is 18. If you take 6 out, you get 12. 9 is less than or equal to 12. So this result doesn't tell us anything. It does not apply. But K33 doesn't have any triangles. It's a bipartite graph. It doesn't have any odd cycles. And so the Girth is at least 4. In fact, it is 4. For triangle-free connected planar simple graphs, the number of edges must be less than or equal to 2v minus 4. And for 2 times 6 is 12 minus 4 is 8. And 9 is greater than that. And the correlation is that K33 is not planar. You might try the Petersen graph, and you might convince yourself that it's not planar. But again, how do we know that you just didn't miss some very clever way of doing it? So in this case, the number of vertices is 10, and there's 15 edges. This does not violate E is less than or equal to 3v minus 6. 3v minus 6 will be 24, and 15 is less than or equal to that. It also doesn't violate 2v minus 4. 2v minus 4 is 16, and 15 is less than or equal to 16. So we can't use either one of those. But the girth is 5, so we can use the actual theorem. In general, E is less than or equal to G over G minus 2, where G is the girth times parentheses V minus 2, and G is 5 here, and 5 divided by 5 minus 2 times 10 minus 2 is 40/3. And 15 is greater than that, is not less than or equal to it as it's supposed to be. And so this proves that the Petersen graph is not planar. These were uses of that theorem. Now let's try to prove it. We want to prove that for a connected planar simple graph with finite girth, the number of edges is less than or equal to the girth divided by the girth minus 2 times the number of vertices minus 2. We do the proof by starting with a census. We go around and ask each region how many edges are in its boundary. Now, each region is bordered by a cycle, and we know that the girth of the graph is G, so the cycles are either length G or larger. The answers we get from each region is going to be G or bigger numbers. And so the number we're going to get is at least R times G. In fact, there's going to be some edges that are not even going to be counted in the census because they might not be on the border of any particular region. So the sum is at least RG. But now we have double counted some of the edges because of the fact that an edge might have been in the border of this region and that region. But at most, we have double counted each edge. And therefore, the number of edges is greater or equal to 2, RG divided by 2. And that means that the number of regions, if you solve for R, is less than or equal to 2E over G. Now we use our handy-dandy Euler's formula that says for a connected planar simple graph, the number of vertices minus the number of edges plus the number of regions is 2. This is a magical formula. We solve for E, and E is v+r minus 2. And instead of R, we can put 2E over G, but 2E over G is greater or equal to R. So we get that v+r minus 2 is less than or equal to v plus 2E over G minus 2. Then we solve for E. So if you just look at the beginning, E is less than or equal to V plus 2E over G minus 2, and you solve for E, and that gives us the answer we want, that E is less than or equal to G over G minus 2 times V minus 2. I also want to tell you that there's actually a bigger theorem, a much bigger theorem, an interesting theorem, that gives us not just a necessary condition, but a necessary and sufficient condition. And for that, I need to tell you what the subdivision of a graph is. So here's a graph, a simple graph, and say that you have two of its vertices, X and Y, and E is the edge. So E is the edge XY, the edge between the two vertices X and Y. What do I mean by insert a vertex on the edge E? I mean actually what you might think. I just want to stick a vertex on the edge E and create two new edges. So what that means is that I'm constructing a new graph. It's not the old graph, it's a new graph. It has one more vertex U, and it doesn't have E as an edge anymore, but it has XU and UY as an edge. A subdivision of a graph is a graph that you obtain by starting with your graph. Your graph walks through the drawer and you want a subdivision. You just start with that. And one by one, you insert a finite number of vertices on some of the edges. And the graph you get, that's a subdivision of the original graph you had. Let's say that you have a graph and H is a subgraph of G. A subgraph of G means that you take some of the vertices of the graph and then some of the edges between those vertices. You can't take an edge without taking its vertex, but you can take a vertex without taking an edge. A subgraph is some of the vertices and some of the edges of the original graph, but if you take an edge, you have to take its vertices. And G prime is another graph, but we know that it's a subdivision of G. There's two easy observations. One is that if G is planar, then so is H. H, remember, is a subgraph of G. If G is planar, that means you could draw G without any edges crossing. Well, if you could do that, you've already drawn H as well, because H was sitting inside G. So then, of course, H is also planar. The counterpositive of that, the same statement, is that if H is not planar, if the subgraph is not planar, then the bigger graph can't possibly be planar either. Another fact is that G is planar if and only any subdivision of it is planar. If you have a planar drawing of G, and if you insert some vertices, that will give you a planar drawing of the subdivision right there. And if you have a planar drawing of subdivision, then uninserting those vertices will give you a planar drawing of your original graph. This is not very profound, but it's a very useful thing. Let me show you how we can use these two little facts to bootstrap our theorem to prove that more graphs are non-planar. So here's an example. This is an 8 cycle with 4 other edges. It's a cycle of length 8 with 4 chords that join opposite vertices. So I have an edge between 1 and 5, one between 2 and 6, 3 and 7, and 4 and 8. That point in the middle is not a vertex. is just where all the edges happen to cross. I could draw this in a different way so that not all those edges cross at the same place, but then there would be more crossings. This is a graph, and I want to know whether or not it's planar or not. Now, I want to prove that it's not planar. So I might use my theorem. V is 8, E is 12. There's 12 edges and 8 vertices. What's the girth? The girth is 4. Here's a cycle of length 4, going from 1 to 2 to 6 to 5 back to 1. There's no triangles, and so the girth is 4. For a connected simple planar graph, you have the number of edges is less than or equal to g over g minus 2 times v minus 2. And if we check that, is 12, the number of edges, less than or equal to 4 divided by 4 minus 2 times 8 minus 2? And the answer is yes, barely. Both sides are actually 12. So the theorem does not apply, and we can't conclude anything. So on the face of it, we can't really use this theorem, but we can. So here's one way to go about it. Here's the graph that I'm wondering whether or not it's planar or not. And this is more an art than a science, in the sense that I'm not going to give you an algorithm for trying to figure out whether or not it's planar, but I can give you a proof that this is not planar. So the first thing I do is that I look at a subgraph. And all I did, I took that edge 1, 5 out. This is a subgraph of the original one because it's just missing one edge. Then I'm noticing that, oh, look, the vertex 1 and the vertex 5 are just insertions of a vertex on an edge. And so I can uninsert them. If I uninsert them, then I get this graph. Okay. And now this subgraph, the second graph that I had, is a subdivision of this new graph. But then if I look hard enough at this new graph that I've got, K33. If I put 3, 6, and 8 on one side and 2, 4, and 7 on the other, then I have a complete bipartite graph on 3 and 3 vertices. And what does that mean? Well, that actually means that all of these graphs are non-planar. Why? Well, because, well, these two graphs are the same. With K33, we already proved using our theorem that it's non-planar. And this graph is the same graph, and so it's non-planar. This second graph is a subdivision of this non-planar graph. Therefore, it's non-planar. And the original graph we started has a subgraph that's non-planar, so it's non-planar. So this original graph is non-planar because it has a subgraph that's a subdivision of a non-planar graph. Now, the amazing thing is Kuratowski's theorem from 1930 that tells us that a simple graph is planar if and only if does not have a subgraph that's a subdivision of K5 or K33. What we just saw in an example was the easy direction of the Kuratowski theorem, that if you have a graph that's a subdivision of K5 or K33, we know that our graph is not planar. Kuratowski's theorem says that if the graph is non-planar, it always will have a subgraph that's a subdivision of K5 or K33. In other words, K5 and K3 are the only obstructions to planarity. Whenever you have a graph that's not planar, then there's a K5 or K33 lurking around. Now, it might not be exactly sitting there, but there will be a subgraph that in itself will be a subdivision of K5 or K33. Okay, this is the end of this lecture. The videos that I have on planar graphs, there's one on tilings of soccer balls and planar graphs, another one on Euler's formula. This one was which graphs are planar, and the next one will be drawing of graphs on a torus. So like and subscribe to my videos. If you want to be subjected to videos like this on your feed, keep hydrated at all times, and I will see you at the next lecture.